Hi, I'm Josh, a student at Abertay, and I'm here to talk about some research that my fellow students and I conducted for our third year project last year. If I can change slides, hold on. Our initial goal was to research and produce a working unikernel to be used in a secure network. Our findings, however, showed that most unikernel implementations were not as secure as many articles and interviews led us to believe. So unless you didn't already know, unikernels are a minimal computing platform that are built with only the features necessary to run a specific application. Because of this, they have the reputation of being lightweight, high performance, and inherently secure alternatives to containers and virtual machines. Due to their low cost, a single host is capable of running multiple unikernels in tandem, making them ideal for small as well as large-scale networking environments. What sets unikernels apart from other virtualized environments is size. So if containers are kind of like mini virtual machines, unikernels are also like mini containers, essentially. To increase the efficiency of deploying and running applications, unikernels function without a general operating system in both their virtual environment as well as on the host's device. Where a normal operating system uses one kernel to run a variety of applications, unikernels use a single specialized kernel designed to only run a single application. Other than increasing performance, this results in a much higher level of isolation between unikernels, compared to the process isolation used by Docker containers. When conducting our research, the majority of our sources led us to believe that unikernels are fundamentally, I believe I am on the wrong slide, hold on. Apologies. So when conducting our research, the majority of our sources led us to believe that unikernels are fundamentally secure, with the potential to revolutionize the security and productivity of cloud environments. The most common of these security claims was that due to their small code base, and therefore small attack surface, a hacker would need to find a version-specific vulnerability to the single application running on the unikernel. This would prevent any hackers from, say, scanning an open telnet port that they could use to exploit. Another benefit is their ability to run multiple instances of an application. Sorry, my apologies. With each instance running different configurations, libraries, and things like that. So like in the example of running multiple databases for a web server, each database can be running with its own different configuration, depending on the protections and privileges for the sensitivity of their content. If a hacker was able to find a vulnerability, however, most unikernels are designed with an immutable infrastructure, meaning in order to change or add anything to their code, the unikernel would need to be completely rebuilt and redeployed. So if a hacker was able to make changes somehow, the unikernel also exists in a virtualized environment, which is completely isolated from the hardware and has little functionality that could be used to further exploit the device. These layers of security would convince most investors that unikernels are indeed extremely secure. However, to some security professionals, there may be some concerns here. For one, as most unikernels only allow for a single application to run, there's a question that what room is there left for like antivirus software or other protections from preventing certain attacks. Another concern is that, as with any virtualized platform, having no direct access to the underlying hardware limits the resources for generating entropy. And lastly, by operating entirely in kernel space with no form of privilege separation, could grant vulnerable applications the right to perform harmful operations. So around the same time we were doing our research, another group had released the work that they had done, showing the vulnerabilities that they had found in many unikernel platforms. One of the most consistent issues that were found was either misconfigured or non-existing ASLR protections. Address space layout randomization, or ASLR, is a security technique used in every modern operating system today, and is extremely important in preventing buffer overflows, which is a well-known security exploit. These vulnerabilities were disclosed in August of 2017, which coincidentally conflicted with a statement made by IncludeOS's CEO a month prior. Well, since IncludeOS was one of the unikernels we were considering to work with, we decided to further research and analyze its security aspects. After replicating some of these experiments, we were able to conclude that many of these vulnerabilities, including a lack of ASLR, still remained even 2 years after disclosure. It should be mentioned that IncludeOS developers have stated that they will address these issues in their 1.0 release, and many other disclosed vulnerabilities have been acknowledged by other platforms who seek to make improvements. So, our method was to run a script that would print out the memory locations of functions, variables, and pointers from a simple Hello World program. After deleting and rebuilding the unikernels files, we repeated this process to verify if the addresses were randomized at each build. So the screenshot included shows the output of one of these scripts, which, as expected, produced the same set of addresses each time. As well as this, we found that IncludeOS implemented no form of page protection or stack canaries, and that all mapped memory was set to read, write, and execute. As we've already discussed, by not implementing memory protection techniques, unikernels open themselves to many forms of attacks, which could result in the last thing you want on your network, remote code execution. So despite the inherent security of unikernels, with their virtualized environment and isolation, allowing a hacker to have such a strong foothold gives them the potential to break out of the virtual environment, crafting malicious packets, or even pivoting to other devices on the network. We also believe that the security claim of unikernels having too few features to be taken advantage of, with no shells or system calls, is quite naive considering the history of exploits that prove any code can be made malicious. Even if a hacker was unable to game a shell in a unikernel, many powerful commands still exist within any coding language, used for, say, running a web server or network utility. This, and the fact that there's no separation between user and kernel space, is of great concern, as most of the security relies on the underlying hypervisor to sustain virtualization. So, why does this all matter? Unikernels, in theory, are ideal for cloud environments, with their inherent security and vast array of benefits. However, due to these benefits, it's kind of easy to forget the features, or lack thereof, which make a unikernel insecure. As this relatively new platform gains in popularity, there is the increasing risk that it will be misused, with traditional security practices being ignored. By praising the security benefits unikernels do have, while ignoring the security features of fully fledged operating systems, endangers the data, services, and infrastructure of cloud or 5G environments developed with this technology. Therefore, if unikernels are to become a more efficient alternative to virtual machines and containers, the fundamental issues and limitations of this platform must first be addressed. So, the most notable of these limitations is the lack of separation between user and kernel space. By not implementing protection rings, processes vulnerable to remote code execution would allow for a hacker to perform malicious actions, bypassing the need for privilege escalation. Similarly, without hardening libraries or networking features of deployed services, unikernels may give a false sense of security, where the running application may negate the small attack surface of the unikernel, while allowing for insecure configurations to exist with minimal protections in place. As mentioned, another significant issue is the lack of memory protections and kernel-based security techniques that are standard in most operating systems. Furthermore, without proper seeding and persistence, a lack of entropy would nullify any implementation of ASLR or forms of generated encryption. Though it's not a major security concern, another limitation we found with many unikernels was having little to no debugging support. This not only delays development, but can also make working with, patching, and security testing unikernels quite frustrating. So, in conclusion, unikernels, as they are vulnerable to known security flaws that have been mitigated in modern computers. These concerns can be expected of any developing technology. However, in their current state, most implementations of non-proprietary unikernels have a lot of catching up to do before they can compete with similar platforms. The current consensus, however, must first change. The security developed for operating systems should not be casually thrown away in the pursuit of efficiency. Security is not and should not be treated as bloat. As well as this, being inherently secure doesn't mean that unikernels are secure enough. And I think some of these experiments prove that. So, despite the criticisms we've made of unikernels, we still do acknowledge they have great potential and are definitely worth a platform investing in. NanoVMs is a unikernel platform that proves this and is a great example of security done right. Their CEO actually comes from a security background and has addressed the vulnerabilities that were disclosed in the 2017 paper, and have an article about this on their website. So lastly, in conclusion, most unikernels have a long way to go in terms of security, but if done well, they might just revolutionize the cloud. So that's my presentation. If you guys have any questions, here to listen.
Thank you, Josh. Yeah, that is just until now. So far, we have one question. Let me put to everyone. I will read it for you, okay? You may have come across Kube's OS, which uses isolated and virtual machines for each application. Do you think unikernels could be a safer replacement or increase the security?
Well, we never actually went into Kube's OS. We tested quite a few unikernels, but that wasn't one of them. So I kind of talked about isolation before. If I can go back to that slide, or actually I'll just say it here. So even if the virtual machine is isolated from, say, its hardware, that doesn't mean that it's isolated from the network it's within. So if you're running a unikernel on, say, some server somewhere, a hacker still might be able to use that to pivot to other devices in the network. So it might be secure, but with virtualization, there's also always the chance that a hacker could find a way to break out of virtualization. I think a couple of years ago, VMware was broken out of using like a floppy disk drive or something like that. So we can see, oh, sure thing. How do I get the slide off?
I think it.
Yeah, that's kind of my answer. If you want to get in touch with me afterwards, I think I could provide a much better answer. My email's just over here.
Yeah, okay. I have one question about the experiment you did. Did you use any specific application with the unikernel? Or it doesn't matter, the type of the application?
It doesn't matter. We just used like a simple Hello World program that we compiled with unikernel. We just had a script that would actually show the memory addresses. And we were able to find that those never changed, even after like rebuilding everything. So
because I was thinking about if the application maybe uses any specific network port. I don't know, maybe it can impact on the experiment.
Yeah, no, I think that's possible.
Okay.
I think ASLR is specifically implemented by the kernel, not the application. Like the application will be ASLR compatible, and then the kernel would implement the ASLR. But we weren't able to observe that at all.
That's good. So if does anyone have any other question? Okay, so thank you, Joshua.
It was a pleasure.
Yeah, thank you very much.